We're going to do, from the looks of things, we're going to do like, we'll get 4 sections in and a test. I hope to do that before we leave for Thanksgiving. Or sorry, 5 sections and a test. Hopefully get that in before Thanksgiving. We'll see. That'd be the last test. Anything after Thanksgiving would just be part of the final. That's the plan right now. We'll see how that plays out, but just trying to piece that together. Today, we're going to be looking at a topic called related rates. This, as a reality check, is one of the more difficult things in first semester. Mostly because of the story problem nature of these things. So it's like calculus story problems. Okay? Once you get the hang of it, they're not bad. It's going to be like the same tricks over and over and over again, but until you've done some and gotten like familiarized with the patterns and some of the tricks and stuff, it can be hard. Just like real talk, it can be hard.
Real talk.
Yeah, just trying to be honest and straightforward. So as much of an A game as you have, you'd want to like try to lock in and bring that A game here for today. I do have 2 days planned to do this, so we'll do like a general lecture with examples, and we'll have a day for you guys to do some additional practice in class. So I am planning for 2 days on this topic. The good news is no new concept, right? The derivative rules are done. We've seen them all. There'll be no new derivative rules. These next 5 sections that we're going to look at are all application. They're all application driven. So like there's some theorem involved. Like what can I say now that I have, this fully kind of worked out derivative piece, but there's no more like derivative rules, like the symbol pushing is like, we've done that part of differential calculus. We're kind of moving into application, and as we finish semester 1, we'll be starting to transition towards, integration, which is the other half of calculus, which is basically just going in reverse direction from a derivative. Okay, so it's like doing the undoing it. But we'll cross that bridge here later. So today, so the textbook has some suggestions here on how to attack these kinds of problems. Number 1, read the problem carefully. I can't overestimate how important it is that you understand the words in the problem. Like read it enough times to like you can picture what's going on. Don't just read it once and try to pick numbers out, or just skim it and pick numbers out. That will not go well for you. You need to read the whole thing. You need to read all the words. You need to go slowly and carefully and make sure you understand like the situation that's going on. Most of these problems have like a physical, real world situation that you can picture in your mind's eye. Really helpful if you're able to do that. On that note, draw a diagram if possible. Many of these problems are kind of geometrical based. So the picture ends up being a triangle or a cone or a circle or a cylinder or a sphere, something like that has like a geometric aspect to it. Oftentimes it's really helpful if you're able to draw a picture and put labels on the picture for quantities and build out some symbols to match up with what you're seeing. Step 3 is introduce notation. Assign symbols to all quantities that are functions of time. Along that road, I would say the same thing you want to do is you want to identify things that are constants versus variables. Why is that going to be important? Because when you take the derivative The way you take the derivative of constant is very different than what you do with the derivative of a variable, right? Okay. Specifically, it says assign symbols to all quantities that are functions of time. Specifically in here, we're going to see rates. Whenever you see a rate in a related rates problem, that is a derivative. So like if it tells you the height of this thing is changing at a rate of 4 centimeters per second, that tells you dh dt is equal to 4. That is the value of a derivative, anything that's written as a rate. And they're going to hide whether that rate is positive or negative in the context of the problem. We'll see some examples going on as to where that becomes important. Express the given information and the required rate in terms of a derivative. So if it's asking then for what rate is the radius of such and such changing when the radius is 7, that's an unknown. You'd want to say, look, what I'm solving for is dr dt with respect to r equals 11 or whatever I said. 5 says, write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. So there'll be certain situations where you have more variables than you do information in the problem. Or if you try to do the derivative with the formula as is, you'll end up with a rate that you don't know and you won't be able to get. So in those situations, you're going to have to eliminate a variable by finding another probably geometric relationship going on in the situation to eliminate a variable before we start differentiating. We'll look at an example here of doing that. 6 says, use the chain rule to differentiate both sides of the equation with respect to t. That basically means when I do d dt of both sides, all the variables that aren't t, you get like a dv dt, a dh dt, a dr dt, whatever as you go. And then the last step is substitute in the given information and solve for the unknown rate. So I have 5 examples that I plan to work through here together. These are pretty typical. They range in fairly simple and straightforward to like increasingly kind of more going on. So let's just kind of start grinding through this. The first one says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so do we understand what's happening? You can imagine this is like blowing up a balloon at a party, right? Okay. What shape should I draw here? Sphere. Sphere is the answer. Circle's close. Okay. What measurements do I need to describe a sphere? Just the radius, right? Everybody's okay there. So far, so good. There's my picture. Introduce the label. What are we interested? What is given to us? So it says the volume increases at a rate of 100 centimeters cubed per second. So that is dv dt is 100 cubic centimeters per second. Everybody's okay with that? How did I know it was positive? Increases. Okay. Sometimes it'll be pretty evident whether it's positive or negative, but they'll hide it sometimes too. And we'll look at an example here in a moment where we're going to hide whether those rates need to be positive or negative. What are we looking for? So what is that going to be? That's dr dt when, well, it says when the diameter is 50. Everybody feel okay so far? Do you know an equation for a sphere that relates volume and radius? Yeah, the volume of a sphere is pi r cubed. But yes, that looks good. Does everybody feel okay? So if I take the derivative with respect to time of both sides, the derivative of volume with respect to time is 1 times dv dt, right? The 4/3 pi is constant, so they can just pull out front. The derivative of r cubed, 3r squared, dr dt. Just like we did with implicit differentiation. Everybody feels so far so good? Okay, what are we solving for? dr dt. Do we know the volume with respect to time? dv dt. 100. Do we know r at that instant? 25. How'd you get 25? Yeah, diameter is 50, so the radius is 25. So now we just solve for dr dt by dividing both sides by all that mumbo jumbo, right? If I do that, I get about 0.0127 centimeters per second. This one fairly straightforward, right? Does that feel okay walking through? That's the volume formula for a sphere. Yeah, if you look at the inside cover of your textbook, I think it has a lot of those volume formulas built in. Yes?
On the test, will the following give us those equations for the sphere?
So on the AP, I think that typically they would give you the volume stuff. If it was areas, I'm not so sure. So like circle, triangle, rectangle, those kind of areas. Probably not. If it's the volume of a cuboid, like a rectangular prism, probably not give you that one either, like length times width times height. So it just kind of, it'll vary a little bit. I would suspect they would give you the sphere formula. But sometimes it's hard to tell. Let's look at the next one. It says a ladder rests along a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Can you guys picture the situation in your head? You know, it's like that, right? You've probably leaned something up against the wall and had it slide out. That's basically what's happening, right? So let's draw a picture. Okay, so it says the 10-foot ladder rests against a vertical wall. The bottom of the ladder slides away from the wall at 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So it sounds like the sides of the triangle are the things that I need to be concerned about. I'm going to call those X, Y, and R. I try very carefully to use X for horizontal things and Y for vertical things. And then I typically use R for radiuses, or radii, I guess is the proper English. All right. It says a ladder 10 foot long rests against a vertical wall. What is that telling me?
R is 10.
R is 10. What else is R? Yes, it's feet, but what kind of quantity is it? It's a constant, right? No matter where that ladder's sliding, the length of it is always still 10. Okay? Is the distance the ladder is from the wall going to be constant? No. X and Y are variables. Everybody's good? Okay. It says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, what is that telling us? Dx dt is 1. Now, how did you know it was positive? Great, because x is getting bigger as this thing slides away, right? It's going in that direction. So the x is increasing. So dx dt needs to be positive. Everybody's okay with that? Now that's hidden inside the problem, right? From the geometric nature of what's going on. They've hidden that. It's nasty when they hide it and it's actually a negative. So watch out for that because it does happen rather frequently. And then it says, how fast is the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? What is that asking for? When x is equal to 6. Is everybody okay with how we've labeled everything? Okay. What equation is going to relate x, y, and r? The Pythagorean theorem. Everybody feel good so far? We'll do the derivative with respect to time of both sides. What's the derivative of x squared going to be? 2x dx dt. What's the derivative of y squared? dy dt. And what's the derivative of r squared going to be? Nope. 0. Why is it 0? R is a constant. So far, so good? Okay, so let's start filling in. So we know x is 6. Dx dt is 1. Oh, we don't have a value for y. Uh-oh, we're short something. Do we have enough information to solve for y? When x equals 6, r is still going to equal 10. The Pythagorean theorem is still going to hold. It's still a right triangle. So we can say that 6 squared plus y squared equals 10 squared. So y is going to be equal to 8. So when I subtract and divide, I get negative 3/4. What should the unit be on this? Feet per second, right? Should be the same unit as dx dt. Well, which direction is the ladder going, right? So I'm not surprised that the rate is negative because it's actually sliding down the wall, right? In fact, that makes sense. Everybody feel good? So far, so good? Okay. A water tank has the shape of an inverted circular cone with base radius of 2 meters, height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate of which the water level is rising when the water is 3 meters deep. John? Yep. So everybody can picture what's going on. Yes or no? Been at a water cooler that has the little cone cups? That's basically what's happening. And you're like filling up your cone cup out of the water cooler. Except this is a giant one. You know, it's like 6 meters wide and 4 meters tall. So it's like a big tank, but everybody can picture what's going on? Okay. So let's draw a picture. So what measurements do we need to describe a cone? Radius and height. Actually, I'm going to write it here. And what's happening to this conical tank? Filling with water, right? So technically, there's a second cone inside of it, right? Now, who hates that we have two things with the same label? I do. I'm going to call this RW and HW for water. And I'm going to call this HT and RT for tank, so that I can differentiate between which cone we're talking about. The cone of water or the cone of tank. Everybody's okay? Does everybody feel happy with the labels that we have in here? Good? All right. It says a water tank has the shape of an inverted circular cone with a base radius of 2 meters. What do I call that? It's not a rate, so it's not going to be a derivative. Like the unit is just meters. That's RT. And height of 4 meters. What's that? HT. What are those? Constants, right? The tank, the cone that's the tank is not changing at all. That thing is constant. The cone of water, that's changing because we're pumping water in and it's getting bigger, right? It says if water is being pumped into the tank at a rate of 2 cubic meters per minute. What is that? What do we call that? dVW dt. So I want to differentiate. That's the volume of water as opposed to the volume of tank. Because we have two cones here, I want to be careful about what I'm naming things so it's really clear to me and I don't get confused. Everybody feels good so far? Find the rate at which the water level is rising when the water is 3 meters deep. What is that asking for? dHW dt when HW is equal to 3. Everybody so far so good? Okay. So we're concerned with this cone of water. What equation relates the volume, the radius, and the height? Volume if a cone is pi r squared times height. So far, so good? Okay. So seems like let's take the derivative of both sides. When I do that, I'm going to get the derivative of VW is 1. Remember, VW is a constant, not a constant. That's a variable, right? The volume of water is changing. We keep adding more water into the tank. Then how do I do the derivative of the right-hand side here? You need a product rule, yes. RW and HW are both variables. So the derivative of HW is just dHW dt. And the derivative of RW, or RW squared, is 2RW drW dt HW. So we have this. Come on. We have this. But what don't we have any information about? Yeah. We don't know RW. We don't know DRW. Can we figure it out? Do we know the volume of water at that instant? Because that's what I would need. We're not given that, are we? Guess what? There's no way to solve for these. What we need to do is we need to eliminate that RW in the previous equation and differentiate again. So what we've done here isn't going to work. Okay? What information hadn't we used to this point? This. Guess what we're going to need that for? Right now. Yeah. So, what other relationship do you notice that's existing between the big cone and the little cone? What? They're similar in what sense?
They're both cones.
Nope.
They're the same heights.
She means very careful. She means the geometric definition of similar.
Yeah.
Specifically, if I look at this triangle and I look at this triangle, those are similar triangles. Everybody's okay with that? Whenever you see a cone problem, this is going to be the trick. So what can I do with similar triangle? What do I know about similar triangles from geometry? They're what? Okay, they're same angles, but what else do I know about them? What? They're proportional, is what you're thinking. Yep. Specifically, I can say that like RT over HT is equal to RW over HW. And I know that RT is 2, and I know HT is 4. So if I cross multiply, I can say 4RW is equal to 2HW, or that RW is equal to HW over 2. So if I then use that to make a substitution, I can say that. Yes, Alex. So HW is not a constant, right? The height is changing. We're concerned about what the rate in which that height is changing at a specific height, but the height is not a constant, right? So this is one of the things that's often hard for students is differentiating between like a variable and a constant, because I'm going to give you the value of a variable at a certain instant in time, but it doesn't mean it's a constant. Do you have a question here?
Yeah.
Sure, go ahead.
Is this supposed to like have this in the
Mm-hmm.
Is this supposed to be like one like in all the same parentheses, or is it like a 1 minus the beginning and then all that divided by?
Yeah, I would use a parenthesis around the numerator and then divided by the denominator.
Okay. I was just making sure.
Yeah, totally fine. All right, so let's clean this up a little bit so it's a little easier to take our derivative now. Is everybody okay? So I'm going to get 1/12 pi HW cubed. Does everyone see where the 12 came from? One over 2 squared is 4 times 3. That's where the 12 comes from. Does everybody see it now? Okay. I just cleaned it up. Now if we do our derivative, it's going to give us dvw dt equals 1/12 pi 3hw squared dhw dt. And here we have everything we need. So we know our dv dt is 2. We know HW is 3. And we know that we're solving for dHW dt. So if I just divide both sides by all that junk, I get about 0.283 meters per minute. Now, in general, when you attempt to use a formula that has the product of two variables in it, very often are you going to need to do a like substitution to eliminate a variable. That's almost always the context. If the two variables are added, more than likely you won't need to do that. But if the variables are being multiplied, like in a volume equation, very often you're going to want to clear out a variable, or possibly one of the variables will be a constant, and then it doesn't really matter, right? But this is the cone situation is a classic got to eliminate a variable type situation. You'll see this, the cone situation, many times in many different like presentations. As soon as you see cone, start thinking we're going to be eliminating a variable. Is everybody okay? For most students, that's like the hardest version of this. Yes. All right. Next one. It says car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour, both headed for the intersection of two roads. At what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile from the intersection? Can you vision and picture what's going on in your head? Okay. So let's call this, let's try draw a picture then. Let's call this spot the intersection. So let's say here's car A, and it's heading in that direction. Oops, I'm sorry, this is car B because it's going north. Car A, let's say, is here, and it's heading west. So it's going in that direction. I know cardinal directions are perpendicular to one another. So I'm going to call this side X, this side Y, and this side R. Pretty good with that. What car A is traveling west at 50 miles per hour. What is that telling us? It's a rate, so it's one of our derivatives, right? Which one is it? dx dt. And what's it equal? Yeah, it's negative 50. Why is it negative 50? Not because it's going west, because as A travels, that distance between the intersection and the car is decreasing. Has nothing to do with the direction the car is traveling. It's that the distance to the intersection is closing. It's getting smaller. Everybody's okay? Very sneaky there, because car B is traveling north at 60 miles per hour is dy dt equals also negative 60, even though it's going up. Because it's closing the distance to the intersection, it's a negative rate. That's very sneaky. If you don't think about it the right way, you sit there and bang your head against the wall and be like, where's the negative sign going and why am I losing a negative sign? Have to think about it as, is this rate closing or growing? Is the distance this rate is describing getting bigger, getting smaller as the car moves in this case? Is everybody okay? Okay. It says both are headed for the intersection of the two roads. At what rate are the cars approaching each other? What is the rate, what is that rate going to be? What do we name that rate? What is representing the distance between the two cars? dr. So this is going to be dr dt. Specifically when x is 0.3 and y is 0.4. Everybody feel pretty good here on how we came up with this? What equation is going to describe this situation? Pythagorean theorem. And we just go take the derivative of both sides. So what's the derivative of x squared? X dt. Everything is almost always for a related rates problem is it going to be dt because time is the thing that's changing. And then y, derivative of y squared. Good. And derivative of r squared. Is the distance between the two cars constant? Yeah, it's not. It's 2r dr dt. Okay. So at this instant, I know x is 0.3. dx dt is negative 50. Y is 0.4. dy dt is negative 60. Uh-oh. What's r? We don't know r. Yeah, we can find r at that instant because we know x and y at that instant. So r is just going to be 0.5. So dr dt is going to be 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60 divided by 2 times 0.5, which is negative 78 miles per hour. So that's the rate in which the cars are heading towards one another, the rate at which the distance between the two cars is closing at that instant, right? Everybody feel okay there? Is this feeling not so bad right now? It's harder when you have to do it on your own. But my hope is that it at least feels doable while we're talking. All right, my last example. A man walks along a straight path at a speed of 4 feet per second. A searchlight located on the ground 20 feet from the path is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Can you picture what's happening in your head? You know, like this is kind of the searchlight. Here's the man. As the man's walking, the searchlight's kind of turning to follow him. Does that make sense? So he's like walking along this path, and the searchlight is just kind of turning along that path to follow him. Does that feel okay about what we're picturing? Okay. All right. So let's say this is the path. Here's the searchlight. And let's just put the man here for a moment. Sounds so far so good. So I'm going to do one of those. So let's call this X, Y, and R. Everybody cool with that? Looks like a triangle. It says a man walks along a straight path at a speed of 4 feet per second. What is that telling us? So, dx dt equals 4 feet per second. And again, we can picture him going this way. It doesn't really matter though. And it says a searchlight is located on the ground 20 feet from the path. What is that telling us? Y is 20, and that's a constant. At what rate is the searchlight rotating when the man is 15 feet from the path closest to the searchlight? This is the key word here. What quantity is this that's changing? It's not R. That's the distance from the man to the searchlight. Yeah, it's this angle here. Let's call it theta. So we're actually looking for d theta dt when x is 15. Does everybody feel okay here? When you hear rotating, you're thinking angle. Okay? Make a note of that. Rotating means angle. It will come up again. Not an uncommon presentation. So, we have x, y, r, and theta. What equation can relate these together? A trig one. Excellent. Which of these, so we have sine, cosine, tangent, secant, cosecant, and cotangent, right? Which one of these sides do we have to have x, right? Have to have x. Because that's the one that we know the instant for, right? So that's going to eliminate which two? Sine and cosecant. Oh, nope. I meant cosine and secant. The adjacent and hypotenuse ones. Everybody's okay? Which is the other side would we like to involve? Because it's going to make our lives easier. Y. Why do I want to involve y? It's a constant. Everybody agree? Which trig function would you like to use that includes opposite and adjacent? Tangent or cotangent? I'm going to pick tangent. It's fine to use cotangent here. And since y is a constant, I'm just going to drop the 20 in there. Everybody feel okay? Do the derivative of both sides. What's the derivative of tangent? Secant squared. D theta dt. Right? What's the derivative of x over 20? One over 20 dx dt. Does everybody feel okay? Now we know dx dt is 4, but we don't know what secant squared of theta is going to be. How am I going to solve for that? Well, I know secant is hypotenuse over adjacent, right? And I know right now x is 15, y is always 20. Can I figure out what r is? How would I do that? Pythagorean theorem. So r is going to be 25. Much easier than trying to muck around with like doing inverse secant or whatever to figure out what the angle is to yuckarooskies, right? So when I type this guy into my calculator, it's 0.128. What is the unit going to be on this, though, for d theta dt? Not degrees. We're in calculus class. Radians per what unit time? Seconds. Why seconds? It was the same unit as it was time before, right? What do you guys think? It's one of these that's doable, but you can see why it's hard, right? What's the hard part? Almost always the setup, right? Getting the setup. If you get everything picture drawn and everything labeled intelligently, usually it goes pretty smoothly. I'm going to be very honest with you guys. This is a kind of problem where I think neatness and organization go a long way to like staying on track and making sure you have everything you need. Some of us that comes easier to than others. If that is not one of your strengths, I would try very hard on these problems to like be as neat and organized as you possibly can. I think it helps enormously to keep everything well labeled and organized, and you have a nice picture that's drawn and labeled, and we're not trying to cram little tiny things in and lose track of stuff, and this makes a big difference. So I think that's a pretty fair spattering of typical related rates problems that varied from pretty straightforward there in the beginning, like nothing sneaky going on, to ones by the end it's like, ooh, that was it tough for me to understand the picture, or like, ooh, you did that similar triangles trick, I wouldn't have seen that without somebody showing it to me first. But similar triangles happen a lot. That's a very common, possibly even set up the equation trick as opposed to even eliminate variables. So I have a handful of related rates problems for homeworks. I didn't bold any of these because, quite frankly, you should do them all. We won't have a homework quiz on this based on this problem set, but I'm going to give you guys, next time we'll take questions from this set and we'll give you guys a worksheet to work on. And we'll take the homework quiz questions from that worksheet for the next class, so you'll have a chance to do these and ask questions and come back and have another round at this before we do a homework quiz on it. Sound fair? Okay. I'm going to be done here. My suggestion for you, got 25 minutes. Like, get some stuff out and try on this while it's still all fresh. The first couple should be fairly straightforward. Give them a shot. Okie dokes.